Hello, my name is Ganesh, and today we are going to talk about SSL and public key cryptography. Let's say there are two entities that want to exchange sensitive information, like a credit card PIN number over the internet. This communication could be intercepted, and the information transmitted could be compromised. Encryption has been used for long to exchange sensitive information. So let's say in this case, the PIN number that is transmitted needs to be encrypted. We simply subtract that number from the maximum possible value for the number of digits transmitted. So we get a value of 8914. This value is then sent over the internet to the recipient. So even if this value is compromised, it doesn't immediately lead to the original value. Now to decrypt this message, the recipient simply subtracts the value transmitted from 9999 and then arrives at the original value. To be able to do that, both parties should know the encryption function. In this particular case, it is a simple arithmetic operation, and the encryption key, which is 9999. Over the internet, it is always not possible to exchange securely the encryption function and the keys. And this is where asymmetric encryption or public key cryptography comes in. So the basis of this is there is a pair of keys, A and B. A can encrypt a message, but it cannot decrypt the message it just encrypted. And only the corresponding key B can decrypt the message. Similarly, B can encrypt a message and only A can decrypt this message. So key B is distributed widely to everybody on the internet, and this is called the public key. Key A is the private key and it is held only by the server. So let's say how a key exchange happens over the internet. So let's say a device on the internet is requesting a domain www.ganesh.com in a secure fashion, which is HTTPS. So it resolves in this server. This server will present its security certificate. A security certificate has some key information like the signature algorithms, the hash values, the issuer, the validity, and a public key of the server. So the client now has the public key, so it chooses an encryption key and it encrypts that key with the server's public key. Because it is encrypted by the server's public key, only the server's private key, which is held by the server, can decrypt it. So even if it is intercepted, that value wouldn't mean anything, or the original information is not compromised. Once the server receives this, it can use its private key to decrypt and arrive at the shared secret, which is the key that will be used for encrypting the communication for the duration of the session. So remember, the actual key is encrypted and the encrypted value is transmitted over the internet, and then the server will decrypt it to get the original shared secret. There is always a question of trust when it comes to communications over the internet. So the request from our device to Ganesh.com could be intercepted by a server on the internet with malicious intent. So this server could present a fake security certificate with the domain Ganesh.com. To overcome this and to ascertain the identity of the server, we use trusted authorities. Certificate authority is a company or an organization that acts to validate entities on the internet, such as websites, and bind them to cryptographic keys through the issuance of document called digital certificate. So in our example, for www.ganesh.com, identifying information such as host name, the validity period, the company name, etc., along with the public key of the server, go into a file that is called a certificate signing request. This file is validated by the certification authority for authenticity, and it is encrypted by the authority's private key. So the golden key, which is the certificate authority's private key, encrypts our server certificate. Now, the public key of the certification authority is widely available on the internet and can be used to decrypt this file. Now, all I have to do is trust the certificate authority. So by default, this is Windows Certificate Manager, and these are all the entities which are trusted by default. So this is called the trust store. In Windows, the certificate manager is the trust store, and in Java, it has its own custom implementation. JKS, P12, and KDB are commonly used trust store. Because we trust these authorities, sometimes these are also referred to as the trusted authority. And the repository of all the trusted authority is also known as the trust store. The key exchange when using a trusted authority is as follows. So the client will make a request to the server, to Ganesh.com, and the server will present a digital certificate. So a digital certificate is the server certificate encrypted with the private key of the certificate issuing authority. Now from the host, there are a list of public keys for trusted authorities, and one of them will be able to unlock this digital certificate, which is basically decrypting their digital certificate. And by decrypting their digital certificate, we will be able to get the public key of the server. Here is a case study of a WebSphere deployment environment with auto renewal of security certificates set, which resulted in an outage. So in this configuration, there is a deployment manager with a 3-node WebSphere cluster. There is also an IHS HTTP proxy, which is controlled by the deployment manager. There are 2 clusters in this setting. One listens on port 9443 and the other one listens on port 9444. One of them has a self-signed certificate managed by the deployment manager, and the other one has an organization signed certificate. So when it was time to renew the self-signed certificates, which is managed by the deployment manager, the deployment manager renewed the certificate, signed it with its root, and updated the KDB file. And it pushed those KDB file to all the nodes and the IHS that it manages. What happened in this situation was that the organization signed certificates, the root certificate of the organization, was missing in the deployment manager's KDB. Somebody had imported the org root certificate into the IHS, bypassing the deployment manager. So this resulted in the IHS not having the root certificate, and hence it did not trust the certificate presented by the WebSphere nodes. So this caused an outage of cluster B. To remediate this situation, the org signed certificate was imported into the IHS trust store and eventually imported through the deployment manager, so that the source, which is the deployment manager's KDB, contained all the information, including the root certificate of the organization that issued the certificate. Thank you.